So again, we're going to start with this definition of a homomorphism. A map phi of a group G into a group G prime is a homomorphism if phi of AB is equal to phi of A, phi of B, where here the binary operation is the binary operation of group G, and over here the binary operation is the binary operation of group G prime. And again, this could be like multiplication, addition, could be several different things. Same thing here, it could be multiplication or addition, depending upon what the group operations are. So suppose f, g, and h are functions, say from z with addition to z with addition. So they're functions from this group to this group. It's the same group under the same group operation. They both have plus. So which are homomorphisms? So let's say we have this one and this one and this one. So we want to test these to see if these are homomorphisms. So again, according to our test, we have to be able to do like a group operation here, like say phi AB, and show that that's going to be equal to phi A, phi B. So let's try the first one. So let's go solution here. Let's consider this one right here. And let's put in two different values, let's say x and y, and put them into our function. And so that means it's going to be x plus y squared. And if we FOIL that, we're going to end up with 2xy plus y squared. And now, according to our definition of a homomorphism, we have to show that that's equal to, say, adding these two functions. So let's take a look at that. So if we do fx plus fy, and if, again, using our definition of our function here, x squared plus y squared like this, we see that these are not equal. And so this f is not a homomorphism. So let's try the next one. Let's try g. So g x plus y is going to be equal to, again, so we're going to put x plus y right in here into our function where x is. So that's x plus y plus 1. So I simply put that into here. And now we want to do the addition of the two functions again, x plus g of y. We want to add those, and that's going to be x plus 1 plus y plus 1, x plus 1, x plus y plus 2. Now we see here, once again, they're not equal. So this one also is not, G is not a homomorphism. So let's try our final one. Let's try our h of x and see what happens there. H of x is equal to 2x. Let me move that up a little bit. So that was CH of x is equal to 2x. And so let's once again do our x plus y. That's going to be 2x plus y like that. Just put this into our function. This is 2x plus 2y. Now we'll try hx, hy. Put those in here. 2x plus 2y. This time they are equal. This time we see the 2x plus 2y, 2x plus 2y. So this, yes, this is a homomorphism. Another example, for any group G, the identity map is always a homomorphism. That is, remember, the identity map would be one, let's say you had phi of x is equal x. You put x in your function and x comes out. And of course, we can test this if we do phi of x, y, let's say, whatever our operation is. Let me just, just use like a generic operation like this. And when we put x, y in by the identity, we're going to end up with xy. And then if we put phi of x, phi of y, we're going to get xy. So the identity map is always a homomorphism. And let's do another example here. So let's say we have phi going from a group G to a group G prime, such that phi of x is E prime for all x, and where E prime is the identity in G prime. And so the question is this a homomorphism? And so let's try this. So again, if we did, say, our phi of x, y, whatever our binary operation is. Now, according to this, it says that whatever you put in here, you're going to get the identity like this. And then if you do phi phi of y is the identity times the identity, which is just going to, of course, be the identity. So the answer is yes. Phi is a homomorphism. Let's consider this function. Say it's a function in the integers, such that if you put in an integer here, you get out a to the n, like this, for some a. So this can be thought of as a function from the integers to some multiples of a. Is this a homomorphism? And so let's check. Phi of n plus m is equal to the a n plus m, like that. And now let's try the individual ones. Phi of n, phi of m. And so this is going to be a to the n, a to the m, which is n plus m. Again, those are equal. So this is a homomorphism. Now we're going to talk about images and inverse images. So let's get a definition here. Image and inverse image. Let phi be a mapping of a set X into a set Y. And let A be a subset of X and B be a subset of Y. The image of A in Y under phi is given this way. So you have this set A, and the image of A in Y under phi is defined as those values that function produced by inputting values from A. And so it's simply something like this. So you have like some kind of a set here. In A, it's a subset of X. Again, it could be all of X or part of X. And then phi maps it to something in Y. Again, Y is over here. And phi of A is here. So just a typical picture of a mapping from you put in some values from this subset A, and they map to this phi of A. And the inverse image of B in Y is phi inverse B phi of X in B like this. So again, let me make a little picture, is probably a better way to understand the inverse image. And so let's say this is Y over here. And then, so the inverse image of phi would be values produced here by the function. So let me sort of map it this way. And so this would be, say, the inverse image. So again, if we look at the definition, those those are values in X such that phi of X was in B. So if you have a set B over here, and phi inverse of B are going to be those values in X that produced values in the set B. And let's look at this theorem. Let phi be a homomorphism of a group G into a group G inverse. 1, if E is the identity in G, then phi of E is the identity and let's call it E prime in G prime. So this is interesting. So if phi truly is a homomorphism and from a group G into group G prime, and E is the identity in G, then phi of E is going to produce the identity, call it E prime in G prime. So a homomorphism will map the identity in one group into the identity of another group. And then also, 2, if A is in G, then phi of A inverse is equal to phi of A inverse. 3, if H is a subgroup of G, then phi of H is a subgroup of G prime. Yeah, so if H is a subgroup of G, then phi of H is a subgroup of G prime. The last one we have is if K prime is a subgroup of G prime, then phi inverse of K prime is a subgroup of G. Proof. Once again, we're assuming that phi is a homomorphism from G into G prime, and also let E be the identity in G, and E prime the identity in G prime. So again, let's start and prove this. So let's start with phi of A. So suppose we have phi of A. Now we can actually call this phi of AE just based on the definition of the identity. And because this is a homomorphism, it would be phi of A, phi of E, like this. So now we have this equal to this. So let me just write that down. Phi of A equals phi of A, phi of E. Now, if we multiply both sides by the inverse, phi inverse A, phi A equals phi inverse A, phi A, phi E, like this. Now, this right here is going to be the identity in G prime because we have the two functions, and these are actually the two functions. So this is going to be E prime, and this is going to be E prime. So E prime, E prime. And now, again, if we just carry this left-hand side down, now, of course, E prime times phi of E will just give us phi of E. And that's what we were trying to show. So phi of E is equal to E prime. Like that. So let's try to prove the next one. If A is in G, then phi of A inverse is equal to phi A inverse. So let's take a look at that. Let E prime be the identity in G prime. And if we have E prime is equal to phi of E. Now we got that one from part 1. Remember, we just did that a minute ago. We just proved that. Then phi. Then we can write this inside as phi A inverse like that, just based on definition of identity. And once again, because it's a homomorphism, we're allowed to do that because of homomorphism. And so what do we have? This is equal to this. And once again, we'll multiply both sides by phi A inverse. Excuse me, I made a mistake right here. This should have a -1 right there. That should be -1. Please fix that. And again, this is going to be phi 1 like this. Again, this, of course, is going to be the identity. And of course, this times this is going to give us phi A inverse. This is going to be the identity. And so we're going to have phi A inverse. And the identity times this is going to give us phi of A inverse like that, which is what we were trying to prove. So let's try to prove this one here. If H is a subgroup of G, then, that should say then, phi of H is a subgroup of G prime. So let's take a look at that. So that was for 3. Let H be a subgroup of G. And let phi of A and phi of B be any two elements. In phi H. Then now we need to show it's a subgroup. And so there's a few ways we could do it. Maybe I'll just go ahead and just show that it's a group. So we're going to first say that it's closed. So if we do phi of A, phi of B is going to be equal to phi A, B. Again, because it's a homomorphism, this is going to be true. Now, and that's going to be in phi of H. Then so that means that phi A, phi B is in phi of H. So it is closed because we took any two elements in phi of H and proved that we put them together, they're going to be in phi of H, so it's closed. Identity. we have phi of E. We already established that that is equal to the identity. So we have the identity. And then also from the previous steps, we have the inverse. We actually, from the steps we just did a minute ago, the inverse exists. And associativity will just come from any subgroup. We'll always get associativity. So we're going to have associativity. Again, because it's a subgroup. So we're going to have associativity because H is a subset of G. So that proves it's a group. Next, let's look at this number 4. If K prime is a subgroup of G prime, then phi inverse of K prime is a subgroup of G. This one's a little bit more difficult to prove, but let's go through that. So actually, let me write this down. Again, we're going to do the proof of number 4. If K prime is a subgroup of G prime, then phi inverse of K prime is a subgroup of G. And so let's say, let me make a little picture of what we might have here. So we have a group G and the group G prime. And then this K prime is a subgroup of G prime. And then it's going to map, the inverse map is going to be back to this over here, which is phi inverse of K prime. So there's going to be an inverse map like this. So again, let's think of what we have here. Again, you're taking a subgroup of G prime, this K prime, and you're taking the inverse function going back here. Now, these points here are going to be produced by points in the group G, and specifically, so therefore when it maps back here, the inverse map is going to be a subgroup of G. And let's write again the definition of phi inverse. It's going to be equal to those values in the group G that produce values in the set K prime. So such that phi of A is in K prime. So in other words, so you have K prime and you have this function that produces values in K prime, and then this inverse function are those values in G which produce the values in K prime. So now let's go ahead and go through the proof. So first of all, let K prime be a subgroup of G prime. So we want to prove, again, we want to prove that phi inverse K prime is a subgroup. So again, we have to go through our steps. We have to start by proving closure. So let's take a look at closure. So let A and B be in phi inverse K prime. And now, of course, we're taking two typical elements in phi inverse K prime, and we're going to need to show that their product is, in whatever the operation happens to be, their product is in phi inverse K prime. So start with this, and then let me write out all the terms. Then this implies that phi of A and phi of B are in K prime, because that's pretty much the definition. If something is here in phi inverse K prime, that means it's something that will have mapped to something in K prime. So therefore, phi of A and phi of B must be in K prime. But notice what we have up here. K prime is a subgroup of G prime, but since K prime is a subgroup of G prime, then we know by definition of a subgroup, the product of these two, whatever the binary operation happens to be, the product of these two are in K prime, because it's a subgroup, which means it's a group. Therefore, there's closure in this subgroup, and so then that has to be true. Then, since phi is a homomorphism, we can say, but from the definition of a homomorphism, we can say that if this is in K prime, then phi AB is also in K prime. And now, so again, since phi of AB is in K prime, that means, so in K prime here, that means there was something in this set back here that mapped to that, specifically AB mapped to something in K prime. In other words, phi mapped AB into K prime. That means AB must be in this set here, and specifically the product AB. So then AB is in phi inverse K prime, which again is this set right here. So think of what we did. We picked two typical elements in phi inverse, and prove that their product was in phi inverse, specifically phi inverse K prime. So therefore, phi inverse K prime is closed. So we proved closure. Next, we have to show that phi inverse K prime contains the identity. So let's take a look at this. Now, we can start with the fact K prime is a subgroup. So K prime contains the identity. And therefore, something had to have mapped to this value here. There must be something back in this set here that mapped to it, because if it's in K prime, something mapped to that set. And since phi is a homomorphism, we know that phi will map an identity from one group to the identity of the other group if it is truly a homomorphism, where this is in phi K prime like this. So in other words, phi is a homomorphism, so phi will map identity from one group to identity of another group. And so this had to have come from this set here. So therefore, that is in phi inverse K prime. So there is an identity in phi inverse K prime. So next we want to look at inverses. And again, remember we're trying to show that phi inverse K prime is a subgroup, so we have to pick a typical element there and prove that it has an inverse. So let A be in phi inverse K prime. Then, what does this mean? That means that if something is in this set, it would have been something that mapped to this, that would map to this set K prime here. So then phi of A is in K prime, but since K prime is a subgroup, then we know that there is going to be an inverse of this in K prime. There is a phi A inverse in K prime. But now, because phi is a homomorphism, there's something we had proved earlier. We know that phi A inverse is equal to phi A inverse, like this. Of course, where this is something back in here. So now what does this mean? This means, again, since this is in K prime and it's equal to this, that means that phi would have mapped A inverse into this element, which is in K prime. So then by definition, this element here, therefore A prime has to be in phi inverse K prime, like this. So once again, we took a typical element in phi inverse K prime and showed that the inverse of that is also in phi inverse K prime. So it does have an inverse. Once again, associativity is just comes from the fact that it's a subgroup, so we don't really have to, that it's a subset, I should say. Associativity comes from the fact that uh, phi inverse K prime is a subset of the group G, and since G was a group, it would have had to have associativity. So associativity always comes along with subsets. Let's look at a couple definitions. First definition of a kernel. Let phi from a group G to group G prime be a homomorphism. And the subgroup defined this way: phi inverse of the identity E prime is equal to the x's in G such that phi of x is equal to E prime. This subgroup is called the kernel of phi prime and denoted by cur of phi prime, cur of phi. So let's see what this means. These are the values in G that map to the identity in G prime is what this really means. So the values in G that map to the identity in E prime, sometimes, in it again, you could kind of look at it like this as well. It would be the inverse of the values E prime. and that's called the kernel of phi. And now we have a theorem. Let G to G prime be a group homomorphism. And let H equal the kernel of phi. So this is that set kernel which we defined up above here. And let A be in G, then the set phi inverse phi A is equal to the values x in G, such that, again, sometimes I use a bar for such that, sometimes dots. So since I use the bar up here, I'll use it again here, such that phi of x equal to phi A then this set is the left and right cosets. In fact, let me write this down. Is the left coset AH of H, and is also the right coset HA of H, like this.